Minerals and rocks. Let's get started. So, what is a mineral? Well, a mineral is an inorganic, naturally occurring solid that has a definite chemical composition and atomic structure. Now, that's quite a mouthful. Let's break that sentence down a little bit. For something to be classified as a mineral, it needs to be inorganic, meaning not living, ever was living, or composed of living matter or organic matter. It needs to be naturally occurring, meaning it can't be man-made. Additionally, it needs to be a solid under normal conditions on Earth's surface. It has to have a specific, definite chemical composition, a unique elemental makeup, and a specific atomic structure. Here are some common minerals, including this sample of potassium feldspar, also known as orthoclase, this sample of sulfur, this sample of muscovite mica, some galena, calcite, olivine, and quartz. Now, one of our jobs is to be able to identify these minerals based on their mineral characteristics. And here's some of the things you should look at. The most obvious is, of course, color. And that's sometimes useful, for example, in the case of sulfur, which is a very distinctive yellow color. However, keep in mind that there are other yellow minerals, and that many minerals come in a variety of colors. So color is not always the most reliable characteristic for identification. We also look at hardness using the Mohs scale of hardness, with 1 being the softest mineral and 10 being the hardness. What we will often do is take a piece of glass, which has a hardness of 5.5, and try and scratch it with a mineral sample. If it leaves a scratch, that means the mineral is harder than the glass. We can also look at luster. The most simple luster is metallic or non-metallic. Streak would be the color of the mineral in its powdered form, and we would test that using a streak plate. Finally, we can take a look at how the mineral breaks. If it breaks predictably, we refer to it as displaying cleavage. If it breaks randomly, it displays fracture. There are also some other characteristics like, is it magnetic? Does it have a taste or odor? Does it glow in ultraviolet light? Does it bubble with acid? As well as a variety of other things that we can look at. So, let's take a look at the New York State Earth Science Reference Tables. This is the Properties of Common Minerals chart. And let's see how it works. It's very simple. Here's the column for this mineral, galena. And you can see from left to right, it tells us it has a metallic luster. It's very soft with a hardness of only 2.5. It displays cleavage and a metallic silver color, has a gray-black streak and is very dense, is used as an ore of lead and in batteries, and is composed of lead and sulfur. Here's another example. This is olivine. You can see it's a much harder mineral, displays fracture, it's non-metallic, and it can be used in jewelry, and you can see its chemical composition right there. So those are minerals. Now, what happens when minerals combine in nature? Well, we get rocks. So minerals are the building blocks of rocks. Now, of course, there are thousands of types of rocks on Earth, and so we need to classify them. And so we've come up with a classification system in which rocks fall into one of 3 types of rock. And that classification system is based on the way in which the rocks form. The 3 groups are as follows: igneous rocks from magma or lava, sedimentary rocks from compacted sediments, and metamorphic rocks exposed to intense heat and pressure. So let's begin by looking at igneous rocks. As I mentioned, these are rocks that form from the cooling and solidification of magma or lava. Let's take a look at the reference table on igneous rocks. So if we zoom in, these are our 17 igneous rocks shown in bold. And you'll notice that there's a whole bunch of characteristics shown on this chart. So let's go through them a little bit. We begin with these top rocks, which are referred to as being extrusive or volcanic. And that simply means that lava erupted on Earth's surface and cooled quickly, forming these rocks. Now, because the lava cooled quickly, mineral crystals within it were not able to grow very large at all. And so what we see are that some of these rocks, formed from lava, have a fine texture with crystals that are less than 1 millimeter in size, like this sample of basalt or this sample of rhyolite. Notice the crystals are very small, almost impossible to see. We also have rocks that cool so quickly that the crystals are impossible to see. In fact, they're non-crystalline or glassy rocks like this obsidian. Sometimes lava cools quickly enough for little air bubbles to be trapped inside. These rocks are referred to as being vesicular, like this sample of pumice right here. But what about when magma, which is lava just inside the Earth, takes a long time to cool because it's so hot inside the Earth? Well, in that circumstance, we get intrusive igneous rocks. Some of these intrusive igneous rocks will cool slow enough for the crystals to grow in the magma deep under the ground between 1 and 10 millimeters in size, like this sample of granite. Notice how the crystals are much larger and clearly visible with the naked eye. Sometimes, if the magma cools very slowly, the crystals will grow even larger, over 10 millimeters in size, like this sample of pegmatite. Notice those large biotite crystals. Now let's zoom back out and see what else the chart tells us. This center area shows us color. The rocks on the left side are lighter in color, and on the right they're darker. Here's density. The left side they're less dense, and the right are more dense. And here's composition. The left side are felsic, meaning they're rich in silicon and aluminum, and the right side are mafic, rich in iron and magnesium. Finally, the bottom of the chart shows us mineral composition. And the way we read this is we simply find the igneous rock we're interested in, like, say, pegmatite, and we look down beneath it to see that it commonly contains these minerals: potassium feldspar, quartz, plagioclase, biotite, and amphibole. Similarly, we could look over here and see that basalt or diabase or gabbro contain other minerals like pyroxene and olivine. And so that's how we read that chart. But there's another chart in the reference table seen here called the rock cycle that also shows us a little bit about igneous rocks, namely that they form from melting into magma and then solidification. So as you can see, there's a lot of useful information about igneous rocks found right in the earth science reference tables. Again, just to review, intrusive igneous rocks have large crystals because of slow cooling. Extrusive igneous rocks have small crystals or maybe even no crystals because of fast cooling. Some of these extrusive rocks may be crystalline or glassy, and others could have air bubbles or be called vesicular. Now, just a quick reminder that the longer the cooling time, the greater the crystal size, the larger the crystals will grow. And so that's what you need to know about igneous rocks. But again, we've got two other types to look at: sedimentary and metamorphic. Let's talk about sedimentary for a minute. Now, these are rocks that form from the compaction and cementation of sediments. Keep in mind that sediments are just bits and pieces of other rocks. The other rocks could be any kind, but if the right conditions exist, bits of rocks may be squeezed under the pressure of water and then glued together with this sticky mineral glue. So let's take a look at our New York State reference table on sedimentary rocks. Notice it's broken into a top and bottom portion. Let's begin with the top here. These are referred to as being clastic rocks, which simply means rocks that, as I mentioned, are made of compacted and cemented sediments. And it's very simple. Each rock is just made of a different combination or size of sediments. Let's go through them. This is a conglomerate. Conglomerate is made of big and small sediments mixed together. As long as those sediments are rounded, it will be classified as conglomerate. If those sediments were angular, I would have a breccia, seen here. Again, a mixture of large and small sediments. Keep in mind, we don't care what these rocks are. We don't care what the mineral makeup is. As long as it's a bunch of different things compacted, cemented together, then we have a sedimentary clastic rock. If the rock is made of sand-sized sediments, appropriately enough, we have a sandstone. Smaller sediments, called silt, will give us a siltstone, and smaller still, called clay, will give us a rock known as shale. And so those are our clastic sedimentary rocks. But we do have some other types of sedimentary rocks. Some of them are called crystalline, like this rock salt. Now this is a rock that forms when you have minerals, like in this case halite, dissolved in water, and then that water is given time to evaporate. When it evaporates, the water leaves, but the crystals of the minerals that were dissolved in it stay behind, and you're left with something like this rock salt. We also have other types of crystalline or other sedimentary rocks. For example, this sample is something called limestone. We refer to limestone as being bioclastic. Now remember, our clastic rocks were sediments stuck together. So our bioclastic rocks will be life, living things stuck together. In this case, we have shells stuck together. This is called a coquina. It's a type of limestone. Another example of a bioclastic rock would be bituminous coal, which is made from compacted remains of plants. And so those are our sedimentary rocks. Let's again take a look at the rock cycle because it sums this up nicely. You'll notice we need some processes to happen. For example, we need existing rocks to be weathered or broken down and to give us sediments. Those sediments can be eroded or moved and then deposited or dropped off and then buried by other sediments. And that weight providing enough pressure and compaction and cementation for the formation of a sedimentary rock. So, just to review, clastic sedimentary rocks are classified according to the size of the sediments that make them up. Crystalline sedimentary rocks, like this rock salt, are formed from the evaporation or precipitation of minerals in water. And then finally, we have bioclastic sedimentary rocks, like this limestone and coal. These rocks are formed from the compaction and cementation of organic matter. So, back to our rocks, we have our igneous, sedimentary, and one more group to look at, metamorphic rocks. So metamorphic rocks are formed from exposure to intense heat and/or pressure. You can take any kind of existing rock, and if it gets forced down by the motion of tectonic plates into the Earth's crust, intense heat and pressure down there will cause it to change or morph into something new. Here's the New York State reference table for metamorphic rocks. Again, you notice there's quite a variety and a large list of characteristics and information here. Let's take it bit by bit. The top section are referred to as being foliated rocks, and these form primarily from regional metamorphism, which is primarily a result of pressure. So I'm going to give you an example of a typical scenario that occurs in nature. We start with this rock, which is known as shale. Now you may recall this was actually a sedimentary rock made of very small clay-sized particles. Well, shale, which is very common on the Earth's surface, might get forced deep underground by the movement of tectonic plates. And under those conditions, the shale would be exposed to increased heat and pressure, and it would be morphed into a rock called slate. Notice they look very similar. Now, if that slate gets pushed deeper underground, it will metamorphose even more and become something known as phyllite. Even more heat and pressure, and we'll get a sample of schist, and even more, and we will get the rock gneiss. Notice the bands in gneiss. That's a very common characteristic. Now, if a sample of gneiss is pushed even deeper underground, the heat and pressure will actually cause it to melt, and then it will become an intrusive igneous rock. So this is a result of increasing heat and pressure within the Earth's crust. So those are our regional metamorphism rocks. Notice something, they are all referred to as being foliated, and what that means is that pressure is causing the minerals within the rocks to almost line up with each other. Now we have two types of foliation. We have mineral alignment, seen here, which is when minerals line up as a result of pressure. And then a severe version of mineral alignment is called banding, seen here. And the only rock that displays banding is called gneiss, and this is a result of really intense pressure. But we also have these non-foliated metamorphic rocks, some of which are still caused by pressure, like anthracite coal, right? Remember, regional metamorphism is from pressure. We'll take a look at that in a moment. Some of these, however, are caused more by heat, something called contact metamorphism, when the rock comes into contact with really intense heat from lava or magma nearby. And then, of course, some could be a combination of heat and pressure, or heat or pressure. Let's take a closer look at this first one, the coal. Now, if you recall, there was a sedimentary rock known as bituminous coal. Well, if you take bituminous coal and you had intense pressure, it will metamorphose into a new rock that looks similar, but is much more dense. And this is called anthracite coal, and it is a metamorphic rock. This same idea can actually happen to other rocks, like this sedimentary rock, sandstone, which we mentioned earlier. Now, if you add intense pressure and heat to that, or if it comes into contact with magma, then it will be affected by that heat and it will metamorphose into a rock known as quartzite. And you can see that right here on the chart. Notice it actually says metamorphism of quartz sandstone. The same thing would be true underground. Notice we have some layers of sedimentary rock here. Maybe one of those is sandstone. And then one day a magma intrusion forces its way up, and wherever the magma touches the other rock, it's going to cause some contact metamorphism. That's where you would find your quartzite or your hornfells, or even a rock like marble or metaconglomerate, all forming from contact metamorphism. So those are our metamorphic rocks. Keep in mind that the key characteristic to look for with metamorphic rocks is banding. You will not see banding in any other type of rock other than metamorphic. Again, let's look at the rock cycle in the Earth's crust, and you'll notice that it clearly shows that metamorphic rocks are formed from intense heat and or pressure. And so again, you see this whole rock cycle comes together where any type of rock can be affected by changes that will turn it into any other type of rock. Igneous can be weathered and turn into sediments, which can become sedimentary rock. Igneous could also be exposed to heat and pressure, turning it metamorphic. Igneous could even melt and form a new igneous rock. And so that's how the rock cycle works. Rocks have been continuously changing from one type to another throughout the history of the Earth. And that's about it for rocks and minerals. Thanks for listening.